Functions, interpreting functions, we are going to model quadratic functions with real life situations. If you can read that. Model quadratic functions with real life situations, okay? And of course it's debatable whether these are real life situations, like the farmer. I mean, I suppose if I were a farmer, I might mathematically put together the fence. Probably not. No, you know. Okay, so first of all, a ball is thrown up into the air, and its height over time is described by negative 16t squared plus 48t plus 6. Now, before I do this problem, it's really important everybody knows that, keep in mind, the ball is being thrown straight up. Okay? Because it's height over time. Does that make sense? We don't care about where it goes. We care about how high it is over time. So when you take a look at the graph of this, you're going to have time and you're going to have height. And of course, if it starts at 6, which is like 6 feet in the air, and you throw it up, even if you watch my pen, if you throw it straight up, straight down, it's moving across in time, right? And that's why it looks like a parabola, okay? It does not travel this path. This is not its path. This is its height over time. It goes up, then it comes back down, and time must expire, okay? It's basically a physics problem, okay? So, a couple of things we want to do. One, if we want to find the maximum height, there's two ways to do it. One, we could graph it. Your book's over here, Kurt.
Oh, really?
Yeah.
Oh.
There you go. So we could graph it. We could use our calculator. We could use our maximum, and that is fine. There's nothing wrong with that. A fast way for me is just to use the vertex. So I'm going to use the t equals negative b over 2a. All right, I'm going to use the formula. You could put it on the calculator, but the formula works fine with me, okay? So in this case, the time is going to equal negative 48 over 2 times negative 16. Okay? Which is positive 48 over 32. And I think that's 1.5, but I'll double check. I think that's 1.5. 48 divided by 32. Yeah, it's 1.5. So 1.5 seconds. And that makes sense. When you throw a ball up in the air, second and a half, it's its highest spot, right? Okay, now what's that height? What's that height? Yeah. Marie's totally right. So let's plug it in. So let's go h of 1.5 equals negative 16 times 1.5 squared plus 48 times 1.5 plus 6, right? And again, I'm just going to use my calculator. Want to see another little trick? I'm going to show you. Want to see a cool trick? 1.5 is my last answer, right? So if I go negative 16 times answer squared plus 48 times answer plus 6, the answer is the 1.5. Or you can type in the 1.5. I'm always here to show you new tricks, right? But this A and S has to be the 1.5 because that's the last answer. So boom, okay, 42. So I get a height of 42. So 42 feet. Okay, so there's my height and there's my time, okay? Now, when will it hit the ground? So when it hits the ground, the height is 0. So let's set it equal to 0. 0 equals negative 16 t squared plus 48t plus 6, right? So if it won't factor, and this one doesn't look like it's going to factor to me, there's a couple of things we could do. We'd use the quadratic formula, which I don't think you want to do that. We could graph it and use our zeros, right? So let's see about graphing it, all right? So if I go into my y equals, clear it, negative 16x squared plus 48x plus 6, right? Let me fix my window. My window, 0 to, well, how long do you think it's going to, how many seconds do you think before it hits the ground? Give me an intelligent answer. And how many seconds before it hits the ground? We throw a ball in the air. Give me an intelligent answer. 5. 5 sounds great. Okay, 5.
6.
6 sounds great too. If you told me 100, I'd say, okay, if we're going to be waiting around for a while, right? How high does it go? Well, we already know it goes 42 feet, right? We already know it goes 42 feet, so my window, make it 50 so I can see a little bit more. Is that, you with me? We already know it goes 42 feet, so my max is 50. Okay, so let's graph it. Okay, there it is. So if I want to find out when it hits the ground, right, I just could find this value. So we have a 0, second calculated 0, right? So I went to my 0. Yeah, it will be exact. Yeah, great question. Well, no. No, it won't be exact. It won't be exact, but it's going to be close enough. Good question.
Like, so do scientists who are trying to like calculate like spaceships and things calculate?
Okay, real quick while I'm doing this, there's a great there's a great lesson in this. We lost about 10 years ago. We lost a Mars ship on Mars because they rounded too much, and it came in too fast, went smash because they weren't exact enough. Guess. And so at 0. So 3.12, there could be, so Lane, there could be a square root equivalent of this, but we're just going to go for practical purposes about 3.1, okay?
I said 3.2.
You're pretty darn close, okay? So we got t equals 3.1 seconds, okay? Now domain. Domain of the flight. What does domain even mean? Huh? And?
It's the distance.
It's this distance, which is time. Time. So let's think. Time in the air, right? So domain's got to be time in the air. Time in the air. That's our domain, right? Domain is this. You're totally right. Elijah, domain's this, and this is time, right? That's our time. So what is the time in the air? I throw the ball up. It goes from 0 to 3.1. So my domain is less than 0 is less than t, which is less than 3.1. And I put less than, not equal to, because when it's on the ground, it's not moving. That's why I don't put equal, okay? You all right with that? If you put equal, I wouldn't count it wrong. But the moment it hits the ground, it's not moving anymore, right? So that's why I didn't put an equal. Same thing here. If time hasn't started, it hasn't moved, right? Okay, there's my domain. What about range?
That's the height.
It is the height, right? So the height of the ball, right? So what's the lowest height of the ball?
6.
No.
0.
0, right? 0. And what's the highest height?
42.
42. So the range is just going to be from 0 to 42. And I can include the 0 and I can include the 42 because it really does have a height of 0, right? And it really does have a height of 42, okay? I guess I used interval notation on both. I could use this as 0 is less than or equal to h, which is less than or equal to 42. There you go, set notation, okay? So graph the height of the ball with respect to time. We do not have to be fancy graphers, okay? We just need important things on there. So if I'm going to do my graph, again, we don't have to be fancy graphers. 1, 2, 3, there's time in seconds. 1, 2, 3. Height. I got to get it to 42, right? So I'll probably go 10, 20, 30, 40. Okay, so we just need the height. Starts at a height of 6, right? Because we throw it, it leaves our hand at 6 feet, okay? And then it's going to go up, and at 1.5 seconds at 42, right? At 1.5 seconds it's at 42. 3.1 seconds it hits the ground. There it is. Okay. Thumbs up? That one didn't seem so hard. Again, if you want to graph it, you could have got your max, calculate your max, doing the calculator, right? I preferred to use the math because I thought it was easier, but you could get the max using the calculator, right? You guys know how to do that, right? Enter and enter, enter. So there it is also, right? There's another way to do the max, right? Now, turn the page. Okay, Farmer Bill. So Farmer Bill wishes to create a rectangular field using 100 meters of fencing. Aha, but I got a barn. So if I use the side of my barn, I can use more fencing, right? So, and I want to make a rectangular farm just because it's just easier for fence posts. You guys agree? I don't want circular to be a lot harder, a lot more fence posts. So I just want to make a rectangular barn. So first of all, let's draw a picture. Let's see what this looks like. So here's my barn, and here's my fence. Okay. I'll make it a rectangle. Okay. Since it is a rectangle, we don't know the width. Let's just call the width W, okay? W. So what's left here to put on my fencing is what I didn't use. So what I used here and here, I can't use here, right? So what goes here is what's left over from these two pieces, which would be a 100 minus 2W, right? And if I'm going to build this fence all the way around. An example. If this were 10 and this is 10, I'd have 80 left over, right? 10, 10, I'd have 80 left over because I got 100. Does that make sense? If I make this 20, 20, this would be 60 because that's what's left over, right? Well, I don't know what it is, so it's going to just be 100 minus 2W. Now, area. So area thing, okay? So area is length times width, right? So it's going to be a 100 minus a 2W times a W for width, okay? Now, I want to maximize this thing, so I'm thinking, all right, let me go ahead and do a little bit of math, and if I were to multiply it through, A of W is equal to a 100 W minus a 2W squared, right? So we got two ways we could graph it. Works fine. Works fine. Nothing wrong with that. I'm going to do it the other way. I'm just going to use my negative b over 2a, so I'm going to say, all right, maximum. So I'm going to go, let's use my negative b over 2a to give me the top of the parabola, because we know it's going to be a parabola, right? It's going to look something like this. We need that value there, which is the vertex, right? So I'm going to use the vertex formula. Yes, you can graph it. Okay, so I'm going to go negative 100 over a 2 times a negative 2, because there's my b. And there's my a. I think somebody said, isn't a always the one with the x squared? Yes. I think that was Elijah, right? Yep. So then I get a 100 divided by 4, which is 25. Okay, what does that tell me? Well, I'm going to go build my fence. So if I go to my fence, this side's going to be 25, right? This side's going to be 25. And this side's going to be 50, okay? So I go out there and I build it, and I get it. Okay, so then what are the dimensions? 25 by 50 by 25. Go build my fence, okay? Now, what's the domain of this function? Domain, what does that mean? Yeah, domain's the x values, right? Domain's the x values. But we don't have an x value. What's the x value in this case?
W.
W, okay? So the domain is my width. All possible widths. All possible widths, okay? Every possible width. So, what's the smallest width I could use in this fence? Very smallest. I mean, I could technically almost make the width 0. Almost, right? And then it'd be super long and skinny. It wouldn't be a very good fence. But that I could make that fence. Couldn't I build it? I could make it like this wide and it'd be super long, right?
Yeah.
I don't think I'd get a cow in there or a horse, but I could build that fence. So the very smallest width would be 0. Okay? Does that make sense? Domain is what are all the possible ways. It doesn't mean it has to be a smart way to do it, but it's possible to build a fence with a width that big, right? Now it wouldn't be 0. Yeah, you're on the right track. Okay, it wouldn't be 0 because if I have 0, it wouldn't have a rectangle. Does that make sense? So it's got to be bigger than 0. Okay. Now, what do you mean by straight line? Okay. What if the width? What's the biggest the widths could be?
25.
You're close. Who said 50? Because if I use 50, 50, I've used up all of my wire, haven't I? If I go 50, 50, it's going to look like this, right? Does that make sense? So the biggest I could make my width is up to 50. 50 of it here, 50 of it here. Would make it only this wide, this narrow, right? I mean, it would be super long and skinny, but all of these variations could be built. What's the best option? The best option is obviously to make the width 25, right? Make the width 25 is the best option, but you could build any of these fences. That's what the domain is. What are all the possible, okay? Taylor, put that away, please. So, homework, here it is. Let's write that down.